Recording. Yeah, today what we're going to be talking about, we're going to talk about number systems. So far in our lives, whenever we talk about like numbers, it's like what to do. You come into your school, if we're given a number, and like two numbers basically, we could add, subtract, and do all those things. But what those numbers actually mean. So let me just start off by like a very simple example. So let's just say I have this number. It's a very similar number. We all have seen numbers like this. What does it actually mean? What it actually means is I can decompose this to something like 4 times 10 to the power 0 plus 5 times 10 to the power 1 plus 6 times 10 to the power. Right? I can write it that way because this guy over here is 600, this is 50, and this is 4. That's exactly 654. So look what just happened. I wrote a number, right, as a summation of a bunch of coefficients. Let's just call these things coefficients. Right? Times a bunch of powers of 10. Right? We call this 10 base, and we call this guy, and this guy, we call them exponents. Right? Basically, mathematically, if I want to write it, I can write it as summation I from 1 to n, some coefficient ci times 10 to the power of I. Right? Are you guys familiar with this notation? Yep. You guys on the Zoom, have you seen this notation? Okay. So if you look at it, basically there is a coefficient, and there is a base, and there is an exponent. Right? Look at this base. This base here is actually 10. Right? So whenever we have a number, we're writing it in base of 10. We call this thing decimal representation. So whenever the base is actually 10, then that's basically a decimal representation. Right?
Shows it as even I start from 0.
Correct. Yes. Thank you. So here's the question. I said if the base is 10, that's called decimal. Can I have other bases? Yeah, I can have whatever base I want. In this course, again, last time we said the only thing that we care about is zeros and ones. Right? So what if the base is actually 2? If the base is 2, basically I have to replace all these 10s by 2s and the powers of 2 and represent this number in terms of that. We call that binary representation. Well, let's talk about this decimal representation a little bit more. Look at this representation over here. Look at the coefficients. What's the range for the coefficient? Can this coefficient actually go above 10? No. Because if it's more than 10, then I can add like 1 more, for example, to this one. Or like 1 more to this one. So it never goes above 10. So in this representation, all the coefficients, CIs, they actually belong to 0, 1, 2, up to 9. Right? Basically, all these coefficients are less than 10. Right? Exact same thing should apply here. Right? If I have base 2, if something's more than 2, I can actually carry it over. Right? So in binary representation, what's the range for CI? 0 and 1. We only have like 2 possibilities. Right? So, all right. Let's just do an example. If I gave you this number, I could have written it this way, and that would have been the decimal representation. So let's just say I have this number, and I want to know the binary representation. Right? So I have 6, 5, 4, and I want to know the binary representation. So I'm going to give you guys like 2 minutes to think about it, and then I'm going to like explain how to do it. Again, the whole idea here is I have to write this 654 in terms of powers of 2 multiplied by some coefficients, and those coefficients are either 0 or 1. Right? Why not 0 and 2? Because if Ci is 2, okay, let's just say over here, that's basically Ci 2 to the 1. If Ci is 2, that is already 2 to the power 2. So I can carry it over to 2 to the power 2. I make smaller. It should be smaller than 2, right? 0 and 1 basically means it's smaller than 2. And these coefficients are always positive. For now. All right. To be able to write this guy in terms of basically a bunch of coefficients multiplied by the powers of 2, let's actually look at this guy and see what this guy actually looks like. Right. So what is the decimal representation of 2 to the power 0? It's 1. Right? What is the representation of 2 to the power 1? It's 2. How about 2 to the power 2? It's 4. 2 to the power 3? 8. Right? 2 to the power 4? 16. 2 to the power 5? 32. 2 to the power 6? 16. 2 to the power 7? 128. 2 to the power 8? 256. 2 to the power 9? 512. 2 to the 10? 1024. 2 to the 11?
2,048.
And you can go. For this class, you're actually required to know all these numbers. You got to memorize them. It's not really difficult. Right? Okay, now I know like this decimal representation of these numbers. So I can actually write this in terms of all these numbers. Right? Let me do it. So if I do it, it turns out I can write this as 1 times 2 to the power 9 plus 1 times 2 to the power 7 plus 1 times 2 to the power 3 plus 1 times 2 to the power 2 plus 1 times 2 to the power 1. Right?
So,
look at this representation. There are some elements missing. Right? I don't have 2 to the power of 8. I don't have 2 to the power of 0. What does that mean? It just means the coefficient is 0. So there are actually like some elements here that I'm not just writing, like this. Or like for example here, there is 0 times 2 to the 8. I don't have 0 times 2 to the 6. I don't have 0 times 2 to the 5. I don't have 0 times 2 to the 4. I'm just not writing it, because the value is just 0. Right? So what is the binary representation? Well, I just need to like read off these numbers. If you look at it here, this one corresponds to 10 to the power 2. This one's corresponding to 10 to the power 1. And this is corresponding to 10 to the power 0. So with this logic, if I put everything together, what do I get? 2 to the power 0, that's a 0, so I have a 0. 2 to the power 1, I have a 1. 2 to the power 2, I have a 1. 2 to the power 3, I have a 1. 2 to the power 4, I have 0. 5, I have 0. 6, I have 0. 7, I have 1. 8, I have 0. And 9, right? So this guy over here, basically that's the binary representation of this number. And the way that we can actually distinguish these two things by putting like a little 2 down here to actually say this is in base 2. If you want to be very, very like meticulous and careful about what we're writing, we actually need to put a 10 down here, right? But since we all are used to like using base 10, we always like drop it, right? So is that clear how I actually wrote this number here? In a little bit, I'm actually going to tell you how you can write this thing without actually like decomposing it this way. Okay, we're going to talk about like an easy way of computing it. But for now, let's just talk about the concept. Right? Is that clear? What's going on? You guys on the Zoom, is that clear? Okay, cool. Look at this number over here.
Excuse me, Professor.
Sure.
So in the chat earlier, it said that 2 to the 11 is 2048, and you wrote 2058. So
Oh, that's 2048.
Yes.
Correct. Yes. Thank you. I don't know how I got to 58.
Yeah, so
Yeah.
I have a question.
Sure.
So decimal representation and binary representation are two different things, right?
There are two different representations of one number.
Yeah.
The number is 654. If I want to like represent it in base 10, that would look like this. And if I want to represent it in base 2, that would look like this.
So in this class, are we going to be just focusing on binary or both?
For the representation,
Yeah.
we're going to have to learn how to go from decimal to binary, decimal to hexa, and decimal to octal. And back and forth, we got to go back and forth. Okay, I'll do that. guy over here. This guy over here is actually huge. And as this number actually gets bigger, this number gets bigger and bigger, right? So it's actually kind of not efficient to like just work with like these numbers that are super big. So instead, we can actually look at like other bases, right? Again, in this class, we care about binary numbers. So the bases that we're going to have to look at should be powers of 2. So what we care here, what we're going to actually like focus on in this class, is just going to be base 8, which is 2 to the power of 3, and base 16, which is 2 to the power of 4. So other bases. Base 2 to the 3, which is 8. And base 2 to the 4, which is 16. See, all these things have names, right? We call this decimal, we call this binary. If we do it base 8, we call it octal. And if we do it 16, we call it hexadecimal. Right? We usually show it by oct and hex. Right? Look what's happening here. This is 2 to the power of 3. So if I have like a binary representation, let's just say I have this binary representation here. Let me just rewrite it. Let's just say I have this binary representation, right? What is this thing? This is 2 to the 0, this is 2 to the 1, this is 2 to the 2, this is 2 to the 3, 2 to the 4, and all the way to 2. Right? So what I would like to do is, I would like to write it in terms of 8, and base 8, which is basically 2 to the power of 3. So how can I use this representation to actually write it in base 8? Well, if you think about it, this basically tells me I have to think of every 3 of them and then put them together as like one element, right? But how can I do that? Let's talk about something really quickly before we get there. This is base 8, right? What is the range for the coefficients? With the exact same logic, if it was base 2, the range was less than 2. So over here, the range should be less than 8. Right? So the numbers that I can get, they are 0, 1, 2, 3, 4, 5, 6, and 7. Right? So if I write this number in terms of octal, then my coefficients must be less than 8. Right? How about hexa? What's the range for the coefficient there?
0.
Exactly, 0 to 15. But how can we actually show it? How can I show, for example, 12? I cannot write 12, right? So we come up with like a notation. If this coefficient is 0 to 9, then we're going to have 0 to 9, right? But as soon as we have 10, then 10 is corresponding to A. 11 is corresponding to B. 12 is corresponding to C. 13 is corresponding to D. 14 is corresponding to E. And 15 is corresponding to. Right? Any questions so far about the notation that we have? Oh, that's just a notation. I define, so whenever I see a 10, I automatically replace it by an A. It's just a notation. If I see like 13, I change it to D. Because I cannot write 13 times, for example, 16 power 4, for example. It looks kind of ugly. And that's why we actually change it to like D. Thanks.
So you cannot do linear representation of odd numbers with 2, right? Because of 2.
Odd numbers? Yeah, you can do it. Yeah.
You don't always give an even number because you use it to.
No, you remember that over here you have like 0 times 2 to the power 0.
Oh, okay.
And I can give you like odd numbers. Right? Any question on the Zoom? Yes, it must be capital letters. Yes. The convention is capital letters. All right, cool. So knowing these two, knowing if I have octal, the range for the coefficient must be less than 8. And if I have basically hexa, the range must be less than 16 for the coefficients. I'm given the fact that this space is basically 2 multiplied by itself 3 times, and this guy is 2 multiplied by itself 4 times. I can basically look at this and immediately write the octal version and the hexadecimal version. How? Again, this is 2 to the power 3, so I can divide this thing up by every 3 of them. Right? If I do that, what is this number? What is this number in octal or in? Well, look at it. That's basically 0 times 2 to the 0, right? So it's 0. 1 times 2 to the power 1, so it's 2. Plus 1 times 2 to the power 2, so it's 4. So this guy over here represents a 5. Right? How about this number? What is this number? This number is 1 times 2 to the power 0, right? Times 0 to the power 2, times 0 to the power 0 times 2 to the power 1, and 0 times power 2. So that's basically it. Look what's happening here. For every chunk that I have, I'm going to represent it in terms of an octal number. So over here, if I represent this number in octal, it's a 5. If I represent this number in octal, that's a 1. If I represent this number, what's this number? In octal, what is this number? That's 0 times 2 to the 0 plus 1 times 2 to the 1 plus 0 times 2 to the 2. What is it? It's a 2. So this number here is 2. How about this? What is this number? If you look at this number, that's only 1, right? But if I actually pad 2 zeros here, would this number change? No. Because 0 behind any number would not change anything. Go back here. If I put a 0 here, would this number change? No, it's still 654. With the exact same logic, I'll have 2 zeros here. Now it looks like a 3-digit number. So I can actually find the octal representation.
So 5, and that is 6 because 2 there is 0 times 0, so that's
0.
And then 2 to the
Let's see.
Yeah.
I know what's with me in numbers today, but
So, so just divide it into 3 times, and then you just
Yeah.
to the 0, to the 1, to the 2,
Yeah.
and then repeat it.
I'll basically look at every chunk and write it in terms of octal.
And then you get these numbers.
I get these numbers.
And then these numbers are they coefficients, or are they exponents, or what are they?
They're the coefficients.
They're the coefficients for
Yes, so there should be less than 8.
Okay, and then they're coefficients for octal.
Octal representations, yes. So what's this number then? What is it? It's 1 times 2 to the power of 0. So it's 1, right? So if I put these numbers together, what do I have? I have 1, 2, 1, 6, 8, right? So that is basically the octal representation. How about the hexa? Can I do the same thing? Yeah, of course I can. It's just a multiple of 2. But instead of like 3 times, I have 4 times. So instead of like dividing it by 3, I have to divide by 4. And then write that representation. So let me do that. Right. So I have to divide it up by chunks of 4, right? So I have this guy here, this guy here, and then done. Right? What does this number represent in hexa? What is this? That's basically 0 times 2 to the 0, plus 1 times 2 to the 1, plus 1 times 2 to the 2, plus 1 times 2 to the 3. Right? This guy's 2 to the 3, this guy's 2 to the 2, this guy's 2 to the 1, and this guy's 2 to the 3, 2 to the 0. Right? What is this number? That's 2 plus 4, that's 6, and 8, that's 14. What is 14? So this guy over here is at E. Right? How about this number here? What is this? It's very simple, right? That's 1 times 2 to the 3. That's 8. Right? The rest of the coefficients are 0. How about this? Again, I have 2 digits here. It doesn't look like 4 digits number, but I can fix it very quickly. I can add 2 zeros here without even actually changing the number. Right? What is this? What is this number? That's 1 times 2 to the 1. Right? So what is a hexa representation? That's basically 2, 8. Right? Any question?
How did you get the 8 for the?
Right here. It's 0 times 2 to the 0, plus 0 times 2 to the 1, plus 0 times 2 to the 2, plus 1 times 2 to the power 3. Right?
Got it. Thank you.
Sure. You don't see what's written on the left port? Let me see. That's not. I'll try to write it a little bit bigger so you can actually see. Any question? Any question about a conversion from decimal to binary and binary to like hexadecimal, octal, or things like that?
So the 2, 8, and B are the coefficients.
Yes, exactly. These are the coefficients. Basically, this, if I were to write it in terms of the summation that we had before, it would look like this. times 16 to the power of 0 plus 8 times 16 to the power of 1 plus 2 times 16. Right? Is that clear to everybody? Is that clear to you guys? You guys on the Zoom, is that clear? Okay, great. So we learned how to go from binary to either octal or hexa. Can I actually do the reverse? If I'm basically given this number in hexa, or if I'm given this number in octal, can I actually go back to like binary? Can I do it? Well, the answer is yeah. Whatever I did here, I can do the reverse. Right? So let's just do an example. Let's just do an example. Let's say I'm given this number. B3, 6, B, and 16. Now what I would like to do is I would like to find this number's representation in base 2. Right? Look what I did over here. Or over here. What I did was, if I had like a binary number, I looked at every basically 4 chunk of it, and then I basically wrote the hexa representation. So I can do the reverse. So I can look at every single element that I have over here, and write the binary representation of it. Right? But how many digits do I need? How many digits do I need to write every single one of these things? We need 4. Why? Because remember, base is 2 to the power of 4. So I need 4 digits. So what is the 4-digit representation of E? First of all, what is E? What number does E represent? 13. So this E here is 14. Right? What is the 4-digit representation of this 14? So if I wanted to write it in terms of binary, how would I write it? Can somebody tell me exactly? Yeah, exactly. I can write it as 1, 1, 1, 0 to the 2. Why? Because this guy is 2 to the 3, this guy is 2 to the 2, and this guy is 2 to the 1, and this guy is 2 to the 0. So I have 0 times 2 to the 0, so it's a 0. 1 times 2 to the 1, so it's a 2. 1 times 2 to the 2, so it's 4. And I have 1 times 2 to the 3, which is 8. If I add them up, that would be 14. Right? That's basically 8 plus 4 plus 2. Right? So I got the last part. So I have 0, 1, 1, 1. That corresponds to this E. Right? How about the 6? How can I write the 6? How can I write 0, 1, 1, 2? Can somebody else actually tell me as well? Yeah. Well, that would be 0, 1, 1, 0. The power 2. Basically the base 2. So I can actually put it here. 0, 1, 1, 0. How about 3? How about 3? I'm thinking 3 is this. Is that correct? It is correct, right? Because I have 1 times to the 0, which is 1, and 1 times to the power, times 2 to the power of 1, which is 2, so that's 3, and the rest is 1. So right over here. And the last digit here is a B. What is a B? First of all, from here I know B is an element, right? What is the binary representation of this element? I'm claiming that's this guy. Right? That is 1 times 2 to the 0, so it's 1. 1 times 2 to the power of 1, so it's a 2. 0 times 2 to the power of 2, so it's a 0. And 1 times 2 to the power of 3, which is an 8. Which adds up to the element. Right? Then I just need to like put it over here. See? This was an hexadecimal representation of a number. And this is the binary equivalent of it. Right? So if I wanted to go from hexa to binary, then I could write the binary representation of every single digit that I have here. And if I wanted to go from binary to a hexa, I needed to divide it up by every 4 digits. Right? What if I wanted to go from octal to 2? What was it? It was the exact same thing, right? I just needed to write the binary representation of every single element that I have. The main difference comes here when I have the coefficients, right? When I'm actually writing an octal, the coefficients do not go above 8, right? So it's strictly less than 8. That's the only difference, right? And if I want to go from binary to octal, then instead of like dividing it by 4, I divide it by 3. So every 3 digits, right? Is that clear? Is that clear to everybody? You guys, so you should get the same number. No, not exactly the same number. I mean, they're the equivalent representation. If you look at the decimal, yes, that's the same number. Yes. Any question before I move on? Is it the same concept if we go from octal to hexa? No. Because if you look at the octal, that's 2 to the power of 3, and hexa is 2 to the power of 4. They're not some sort of like multiple of each other. They are multiple of each other, but it's not the power of 2. What's that?
You can go from hexa to octal and hexa to binary.
Yeah, you can do that, but not exactly this one. This is basically like a shortcut, right? One way to go from, for example, hexa to like octal or vice versa is just to convert it to like a decimal, right? The base 10, and then go from base 10 to like. Or another way of looking at it is that, let's just say you want to go from this guy to octal, right? So you can actually find this representation, this binary representation, right? Then you can actually look at every 3 of them. And that gives you the octal representation. Right? Make sense? Make sense? You guys make sense on the Zoom? I wanted to like represent a binary number, I actually try to divide it and basically write it in terms of basically powers of 2, right? We had like this formula, Ci to the I, right? And I tried to find these like coefficients. But it can be hard, it can be a little bit difficult, right? So if I have like a very huge number, how am I gonna like find these numbers? So let's just talk about like a simple way of actually finding these numbers, right? By the way, this method that we're going to talk about is very, very general. So if you want to find like another, like if you have like a decimal number and you want to go to like any other bases, you can actually use this method, right? The idea here is if I have like a decimal number and I want to find it in base 2, what's happening here? I'm looking for 2 to the power of i's. I'm trying to extract that. How can I extract something from a number? I can keep dividing, right? If I keep dividing and look at the remainders, then that should probably be the same. Not probably, that exactly gives me the same. Right? So let's just do it through an example. So let's just say I have 5, 5, 5, and 5. Okay, it's 5,555, right? And decimal. And I would like to find the binary representation. Like I said, I need to keep dividing this by 2 because I'm trying to find all the powers of 2. And if I keep dividing, I first divide it by 2, then I basically divide it by 4 because I do division twice, right? And if I keep doing this, I basically extract all the powers of 2. You know, like when you're actually like dividing it like in high school or in elementary school, you're actually writing it like this, right? You divide every year and then you basically the remainder and things like that, right? I'm just gonna actually write in a little like weird notation here, but I feel like it actually makes more sense. So the way that I actually like represent division, it's a little different. But it's basically the same thing, right? So instead I actually show it this way. 2, if I divide it by 2, this is gonna be the quotient here. And over here I'm gonna have the divide, the remainder. Right? So if I divide by 2, what do I get? What do I get?
2,500.
This is 2, so that's going to be 4. That's 1,555, right? Right, then I have 7, so it's 14. I have 1, then the other one, again 7, 14, 15, 7, 14, and the remainder. Right? So what I'm doing is I'm basically dividing it by 2. Okay, over here, that's basically the quotient. And over here, that's the remainder. Right? Basically, another way of writing this is 2 times 2,777 plus 1 is 5. Right? You can divide it however you want. Okay? Use the simple way. Right? We care about 2 things. We care about the quotient and the remainder. Right? Look, I divided this thing by 2. Right? So if I divide things by 2, what is this remainder? The remainder basically should go very, very, very right. If you look at it this way. Right? So we call this the least significant digit. Right? What's the next step? Next step is I need to like divide it by 2 again, because I'm looking for 2 to the power 2. So I'm going to divide this thing by 2. Right? If I divide this thing by 2, what is the quotient? it is 1388, and the remainder is 1. Right? And I keep doing this. I keep doing this as long as this guy is bigger than 2. Right? So if I do it, what do I get? I get 694, and that's 0. Divided by 2 is 347, and the remainder is 0. I divided by 2, that's 173, and the remainder is 1. And I keep doing this. Right? And I get to a point, that when I'm dividing it by 2, this quotient is actually less than 2. Right? It's a 1 or a 0. But if I read this number from here to here, right, then that would give me the actual binary representation. I'm not going to keep doing this because this number is actually pretty huge. What I'm going to do is look at a smaller example. I'm going to do the example that we actually started off the lecture. Right? But you got the idea. Right? You keep dividing it by 2, and you're going to look at the remainder. And then if you read off the remainders, and that would give you the actual binary representation. Okay? So let me just actually give you an example that I actually go through every single step of it. By the way, I forgot. Who wants to scribe? Do we have like any volunteer to scribe? That's a decimal. When I don't write the basis, it means it's decimal. Do we have any volunteer to describe? Yeah, you're just going to take notes and type it up and send it to me. Yeah. I know, Cindy, you can. You did it once. Okay, Sin Lim. I hope I pronounced your name correctly. Yeah, you can do it. Please go ahead on the canvas and download the template and type it up and send it to me. Thank you very much. All right. Let's do the example that we actually started off with. The example was 654, right? And again, I'm gonna like put a lot of emphasis on it. When I don't write the basis actually is 10, right? We're used to having them. Okay, so let's just find the binary representation of this guy. I need to keep dividing by 2. So if I divide it by 2, that's 327, and the remainder is 0. Again, this is the least significant digit, right? This number is bigger than 2, so I keep dividing. Divided by 2, I have 163, and the remainder is 1. Right? Again, this number is bigger than 2, so I divide it by 2, that's 81, and the remainder is 1. Right? Again, 81 is bigger than 2, I divide it by 2, I get 40, and the remainder is 1. Right? 40 is bigger than 2, divided by 2, I get a remainder of 0. 20 is bigger than 2, divided by 2, I get the remainder of 0. Right? This quotient 10 is bigger than 2, divided by 2, I get the remainder of 0. Still, this 5 is bigger than 2, so I divide it by 2, I get the remainder of 1. This 2 is bigger than or equal to 2, so I still need to divide it by 2. So if I divide it by 2, I get 1, and that's it. Right? This guy over here, this quotient over here, as we call this least significant digit, this guy over here is actually most significant digit. Which means it's going to go to the left. Right? So I'm going to read off all these numbers. I start with this quotient, and then record all these remainders. So the number would be 1, 0, 1, 0, 0, 0, 1, 1, 1, 0. Right? This guy went here, because that's the most significant bit. And this guy went here, because that's the least significant bit. Right? Is that clear? Does that make sense to everybody? You guys have this, does that make sense? All right, cool.
So this is way easier than like just doing it with like 2 to the power of 0 and 1.
What do you mean?
And then you do like factor it out or you get 2 to
Yeah, this is basically like a simple way to find these coefficients when you're writing it. Right? You want to find these coefficients. And this is basically like a simple way of doing it. Right? And the idea behind it is like, I'm looking for powers of 2. So by keep dividing it by 2, I'm actually like extracting the powers of 2. Right? Okay. What else did you do in elementary school? We were given 2 numbers, and they ask us, add these 2 numbers, right? Can we do like the same thing with these numbers? Why basically all the numbers and like other pieces? Can we do that? Well, the answer is yes. We can simply do that. But just a reminder of what we learned in elementary school, all right? Let's just add 2 decimal numbers. So what if I ask you to add 5 plus 7? You know, in my heart, this is actually like 12. Okay? But how does it actually work? So if you think about it, if I add these 2 numbers, I have this 2 over here, and then I carry over 10 to like the next digit. So I basically have 1 carried over here. And that's how I get like 12. In other words, every number in decimal should be in terms of coefficients that are less than 10, right? But this 12 is not less than 10. So what I do is I keep the 2, which is less than 10, and then carry over the whole thing. Remember, 12 can be written as 2, 1, and the 1, right? So basically, over here, if I had a 10, that 10 could be carried over here and create 10 to the power of 1. Right? This is how we basically add it. Well, we can do exact same thing with other numbers, with other bases. We just need to keep in mind that if I have a number, for example, in base 2, all the coefficients must be less than 2. And it was the exact same thing here. All the coefficients here must have been less than 10. Right? If it was more than 10, we carried it over. We're going to do exact same thing for like other numbers. Let's just do like an example. Let's just say I have 1011. It's a binary number. And I would like to add it to 0010. Right? How would I do that? Well, I have 0 plus 1. What is it? It's a 1. Right? I have 1 plus 1. It's a 2. Can I have a 2? No. What can I have? I can put actually like a 0 here, and then carry 1 over here. Right? Right? Does that make sense? Again, remember, if this one was 12, I needed to like make this 2 plus 10, and then we carry this one. Right? What is this thing over here? That's 0 plus 0 plus 1. 0. How about here? It's again a 1. But is this always the case? Can I always like add two positive numbers? In a little bit, or maybe next lecture, we're going to actually learn that's not always the case. Sometimes, if we do this, we're going to have like an extra bit, right? And we need to take care of it. We say like sometimes, if we add 2 numbers, they actually overflow. What does that mean? It means if I add like 2 numbers, then the value is going to be bigger than what we're expecting. Okay, we're going to talk about it either in this lecture, if I have time, which I don't think I have, or next lecture.
So why wouldn't we put another one?
Because that's like a 4-digit representation of this. If I have like, for example, if this guy was a 1, right? Then I have like a 1 over here, but that would be 5.
So then that one would be 0.
Correct, that one would be 0, and then I have a 1 here, right? And that would be 5 digits.
So if there are 2 binary representations that are 4 digits, they have to be 4 digits, they can't be 5 digits?
No.
Okay.
Yeah.
So they have to be the same.
We can add like a digit over here, but we basically need to throw it out, right?
Also, can we add like a 4?
I'll explain that like in detail later. Let's not basically like go on it right now, right? But let's just like see if these 2 things actually add up right now. What is the decimal representation of this number? It's 11. What is the decimal representation of this one? It's a 2. So if I add these 2 numbers to decimal, I should be expecting to get 13. What is the binary representation of this? It's actually 13, right? So it actually matches that, right? So we good. So far we're good. Before we're talking about like all those details and how we can actually add things, let me introduce something else first. All the numbers we talked about, we only talk about positive numbers. But we have negative numbers as well, right? What if I wanted to represent minus 654? How could I do that? Well, there are 3 different ways of doing it. I'm going to explain like all these 3. And then I'm going to say what the problems with those are and how we can solve it. Okay? The first way of doing it, first way of like representing basically all the numbers that we have, is to just by adding a new bit that can basically tells us if the number is positive or negative. Okay? So the first way is to use sign. Right? For example, if I have, for example, this, what number is this? That's a 1, right? So if I put basically a 1 here, right? That basically makes this number negative, right? And if I put a 0 here, then that makes this number positive, right? So that's basically our.
We'll just change the number if you add a number.
How do we
Like
change the
to
number?
the so we don't have 8 plus.
Let's look at another way of doing that. That's called offsetting. We're going to do that. That's going to be necessary. But over here, what do I have? If I basically see the first bit, okay, and if it's 1, then that's a negative number. And if it's 0, it's a positive. What is the problem with this? There's a very huge problem with this one. Yeah, that's like one of the things, right? But it even has like more fundamental problem. Exactly. If I look at this guy actually represents -1. And this guy over here actually represents 1. If I want to add these two numbers, I should be expecting to get 0. But do I get 0? Let's just add them. What do I get? 1 and 1. That's basically 0. I have 1 carried over here, and I have 1, 0, and 1. Does this number 0? No. This is not 0. What's the main problem with it? We have like another problem with this guy. So when we're working with like a decimal number, how many representations do we have for 0? We only have one representation for 0, and that's 0. But over here, I have two different representations for 0. This guy is 0, and this guy is 0. So I have two representations for 0. And that's the problem. But the main problem here is if I add these two numbers, I should be expecting to get 0, but I'm not getting. Right? What else can we do? So we talked about like this sign bit representation. So like we have some problems. So what else can we do? Another way of like looking at it is by offsetting. What do I mean by offset? Let's just say I have a number that ranges from -8 to 7. Okay? So I have like a 3 digits like binary. Okay? So if we have range from -8 to 7, right? If I add an 8 to all of these, what would happen? The range will go from 0 to 15. Right? The range will go from 0 to 15. Then I can actually represent that number. Right? But what is 8 in binary? That's 1, 1, 1. So I'm actually looking for a number that I can add it to the original number that I have, and I get 1, 1, 1. Right? But again, if I do this, if I basically add this 1, 1, 1 to every element that I have, I still have a problem. And the problem here is still I don't get this. Okay? That brings us to the third way of actually representing a number. And that's called 2's complement. I'm not going to go into detail of this because I only have like a couple of minutes. But I'm just going to like give you a rule of thumb. Okay? So the rule of thumb, to get negative number is basically the following. First, we're going to find a number which added to the original number and results in 1.1. I'm only writing it for basically like 3. Okay, if I have like 4 bits, then that's going to be 1, 1, 1, 1. It's going to have like 4, right? And then add 1 to it. Basically, whatever number that number is, I'm going to add 0, 0, 1 to it. Right? The first step is usually called like 1's complement. And if I put these two things together, it's actually called 2's complement. Right? So next lecture, what I'm going to be doing, I'm going to actually talk about like these 2's complement in a little bit like more detail. I'm going to basically talk about like this rule of thumb that we have. And I'll try to like give you like multiple different ways that you can actually compute this 2's complement. Right? Then afterwards,
Professor.
just give me 1 second. And afterwards, I'll try to basically add and subtract 2 numbers, right? And then we're going to move on to basically a circuit part of it and learn how to build a circuit that does basically the addition and subtraction. Okay? So that's the plan for next lecture. Any question?
So you were just 654 and binary
That's right.
So how do we tell if this is 654 or a negative number which is after that?
So this is a number. This is not a signed number. I didn't tell you this is a signed number. So I have to tell you if it's a signed number or not.
So we can't.
Yeah, you cannot distinguish.
Okay.
I'm going to have to tell you this is
How
a
do we
signed number.
distinguish it?
Yes, I'm going to have to tell you if it's a signed number.
Okay, so every time the most left will be a sign, either a negative or